Welcome, this is Coach Dorf. We're going to continue our discussion about calculus, and today we're going to talk about how the derivative can help us understand more about the graph of a function. So here I have an example of a graph of a function, and what do we know by just looking at this graph? Well, we know here at this red point, we have a local max value, and the local max occurs at x equals -2, and the local max value is equal to 3 in this case, because go over there, I get 3, and down there I get the -2. So a local max at x equals -2, and the local max value equals 3. We also know that I have a local min, x equals +2, and the local min value is equal to -2. I can also talk about where the function is increasing in value. So if I look here at my purple part, from there, my function, the graph of the function is increasing, but f is increasing, and that is on from -infinity to x equals -2. So it's increasing there. It's also increasing on the right side of the graph from +2 to infinity. It's increasing because as x gets larger, the y values are getting larger. All right, and likewise, I can talk about where it's decreasing. It's decreasing on the interval from -2 to 2, because as x gets larger, the y values are going down. So it's decreasing on that part there. All right. And some new terms that we haven't discussed before are concave up and concave down. So concave up is where the graph of the function, it looks like a cup. And so in this particular example, I'm going to write it in blue here, and I'll overlap it here. It's concave up along this blue part. So it's going to be concave up on 0 to infinity. And let's see, what color haven't I used? I'll use a dark green here. It's going to be concave down on -infinity to 0, because it's the upside down of a cup. So concave down, all right? And then the last thing that new idea that we have here, and I'll do this in red, we call this an inflection point. An inflection point occurs when the function changes concavity. So when it goes from concave up to concave down, or from concave down to concave up. So in this case, that is right here at x equals 0. It's changing from concave up to concave down. So those are some geometric terms that you'll need to know. And now we're going to talk about how the derivatives will help us find these if we don't have the graph of the function in front of us. All right, so using the derivative here now. So some of this we know already. So first of all, if the derivative is positive, then what do we know? Well, the derivative represents the slope of the tangent line. So if the derivative is positive, that means the slope of the tangent line is positive. So that means the tangent line looks like this. And if I write that in terms of my graph, it means that my function is increasing. So it's increasing here. So if the derivative is positive, then f is increasing. Similarly, if the derivative is less than 0, since the derivative represents the slope of the tangent line, I have the slope of the tangent line is going down, and it's going down for every point along on certain interval here. All right, so there it's going all the way down on all these. So then the function y equals f of x is decreasing on this part. So f is decreasing. The derivative is less than 0, it's decreasing. If the derivative is greater than 0, it's increasing. What do we also know? Well, if the derivative changes from positive to negative at some x value, we'll say c, then what can we tell? So let's think about this. If the derivative changes from positive to negative, so that means my function is going up. So if it's positive, it's increasing, and then at some point it starts going down. It's decreasing. So it's increasing here and then decreasing here. What happens at the point in the middle? Well, that has to be a local max, because it's going up and then going down. So if you have that situation where the derivative changes from positive to negative at point C, then f has a local max at x equals c. And then likewise, suppose f, the derivative of f prime, changes this time from negative to positive at x equals c, then what's going to happen? All right, so we have it's negative, that means it's decreasing first, and then it's going to change to positive, so it's going increasing. So the graph is decreasing, and then it sweeps up and it goes increasing. What happens at the point where it changes there, you're going to have a local minimum. So if it changes, if the derivative changes from negative to positive at c, then f has a local min at x equals c. And those are things that maybe some of you have already realized. I don't know if we've specifically talked about those, but I think that those fit in really well with the ideas we've talked about. Now let's talk about some things using the new words or new terminology we've talked about, especially in terms of the second derivative. All right, so what else can we say? If the second derivative is greater than 0 on some interval, what can we tell? Well, what does that mean? Here's my curve. Let me just draw some tangent lines here. So here's a tangent line. If its first derivative is positive, then it's going to look like this. What does it mean if the second derivative is positive? Well, the first derivative means the slope of the tangent line. The second derivative is the derivative of the first derivative. So that means we can also think of a derivative as a change, rate of change. So the second derivative would mean the rate of change of the slope of the tangent line is positive. So it's increasing. So the rate of change of the slope of the tangent lines is increasing. So this one again was the first derivative is positive. Now if we're going to look at the second derivative being positive, so that means the change in the slopes of the tangent lines is increasing. So here's a slope of a tangent line. It's a negative, it could be -1. And then here's one where it's still negative, but it's closer to 0. Here it is, the slope is at 0. Here it's slightly positive, and here it's more positive. So what's happening there? The slopes of the tangent lines are going from negatives to positive, so the change in the slopes of the derivative is increasing, so it is the second derivative is positive. What does that tell me about the graph? Well, that would happen if my graph were like this, and it would be concave up. So if the second derivative is positive on some interval, then f is concave up on that interval. And again, the reason is you've got the first derivative is the slope of the tangent line. The second derivative you can think of as the rate of change of the slopes of the derivatives or the slopes of the tangent lines. And so if it's positive, it means it's the rate of change there is increasing. So I'm going from a negative value to a larger value, a larger positive value. And so it's going to be concave up. I also like to draw it this way. The second derivative is positive. So I'm going to write two pluses, because it's a second derivative, and positives because it's greater than 0. And then we get concave up. So it's like a smiley face. That's a quick way to help me remember that if the second derivative is positive, it's concave up. We can now look at the other case. What if the second derivative is negative? Then what happens to f? Well, again, the second derivative is the change of the slopes of the tangent lines. So if it's going to be negative, it's going to be going from some positive values, maybe then equaling 0, and then it's going to start going down. So this is a way that I can think of the second derivative being negative is I can think of it as I'm going from some positive values or something close to 0, and then it's going to be becoming more negative as I go farther over. And so what does that mean about the curve of the function? It means that it's going to be concave down. All right. So in this case, then f is concave down on a to b if the second derivative is less than 0. And the way that I like to remember that is it's second derivative. So I have two of these, and it's negative. So I'm going to use the negative sign twice. And that's going to be my frowning face. Or if you want to think about it, it can also be the stormtrooper from Star Wars. Okay, that gives us two more where we can use the derivatives to help us graph it. We can also use the second derivative to find local max and min. Now, what if I have the first derivative at a point equals 0, then we know it's a critical value or critical number. So if the first derivative at c equals 0, that means it's a critical number. It is a critical number, but it doesn't tell me whether it's a local max or min. It could be a local max or a local min, but it also could just be it's going to be called an inflection point, right? So it could look like this, where there's C, or it could look like this. Oh, let me draw that in red, over in red, okay. It could even look like this. And in all those cases, first derivative at that point C is going to equal 0. So that's not enough information to give me something. But if I combine that with the fact that second derivative at C is less than 0, so what do I get? Let me emphasize that that's a second derivative here. Okay, I have a critical number, so the first derivative at C equals 0, and the second derivative at C is less than 0. What do I know? Well, when the second derivative is less than 0, remember, second derivative at C is less than 0. That means it's going to be then, so it's negative, and I've got the frowny face or the stormtrooper. What's going to happen at that point C? Well, it's going to be a local max. So that's what we get here. F has a local max at x equals C. All right, so you need both of those conditions. You need to have a critical number, so f prime at C equals 0, and double prime at C is less than 0. Well, you can figure out that I've got a similar mirror case here, that if f of C equals prime of C equals 0, and the mirror case, suppose it's greater than 0, what do I have? Well, in that case, I'm going to have, let me kind of these off, that goes to this one here. We're going to do this one. So I have the second derivative at C is greater than 0. So that means I've got my smiley face. And because I know I've got critical number there, it's got to be then a local min. So we have, if the first derivative at C equals 0 and the second derivative of C is greater than 0, then we have a local min at x equals C. So there's really two ways that you can find whether a function has a local min or max. You can do the first way that we talked about earlier in 3 and 4, that if it's going up, if the first derivative is positive and then it goes down because the first derivative is negative, so it's increasing and decreasing, then it has a local max. But you can also do what we just did here in 7, that if the first derivative is equal to 0 at a point and the second derivative is less than 0, then it's going to have a local max. And that's because we're going to have, it's going to be, second derivative is less than 0. That means it's going to be concave down. And the first derivative at C equals 0 means that it has to be at the top of that concave down part, and that means it's going to be a local max. Same thing with having local mins. We can use either one of those. Last thing that we have is inflection points. So inflection points. And what do we recall about inflection points? Okay, so remember, those are when the graph changes from concave up to concave down, or vice versa, concave down to concave up. So it changes concavity. So either going concave up, concave down, or concave down to concave up. And that's going to look something like, let me redo that. If I have my function here, it's going to look something like this. That's an inflection point. So going from concave down to concave up, or you could have this where it's going concave up to concave down. Those are inflection points. So inflection points, either one of these. And what do we know about this? Well, we have that if f has an inflection point at C, it will, that the second derivative at C will equal 0. Okay, notice here, the second derivative equaling 0 does not mean that we have an inflection point. So second derivative at C equaling 0 does not mean there is an inflection point at C. Okay, if there is an inflection point at C, then we will get the second derivative equal to 0. All right, this is similar to what happened in the first derivative. If the first derivative at C equals 0, it doesn't mean that we have a max or min. Go back to the example here. here's where we have here's where we have the first derivative at c equals 0. We could have a max, we could have a local max, a local min, or we could have an inflection point. Okay, doesn't give us enough information. Okay, the first derivative equaling 0 does not give us enough information. The second derivative equaling 0 does not give us enough information to know whether it's an inflection point. But if I have an inflection point, then the second derivative at that point does equal 0. All right, now we're going to use these ideas to figure out some information about a graph by just using the derivatives, and we'll be able to sketch it. So let's look at this example here. We have f of x equal x cubed minus 3x squared plus 4. All right, so let's see. First, find the intervals of increase and decrease. All right, so how do we do that? Well, we 1 and 2 that we did up above. All right, going back here to 1 and 2, there's 1, there's 2. As we look at the derivative, and if it's greater than 0, the function's increasing. If it's less than 0, it's decreasing. Okay, look at the derivative. So we take the derivative, we get 3x squared minus 6x. And now we're going to set that equal to 0 to help us find the intervals. So when does that equal 0? Well, I'm going to factor out a 3x, and I'm left with x minus 2 equals 0. So I get x equals 0 and x equals 2. We're going to use those points now to make some intervals. So we're going to go from negative infinity to the smallest critical number, which in this case was 0. Then we're going to go from 0 to the next critical number, which was 2. And in this case, then we would just go from 2 to infinity. So we have these three intervals, and we're going to look at the derivative of the function here. Now, we just need to take a point in each of these intervals. Because of the way we made the intervals, whenever I take whatever works for one point in that interval has to work for all the points in the interval. Meaning that if the derivative at a point in that interval is negative, then it's going to be negative for every point in that interval. If the derivative at a point in that interval is positive, it's going to be positive for every point in that interval. Okay, that's because the way we found these intervals. We found out where the derivative equals zeros. That then became the endpoints of our intervals. And that means every point inside each of those intervals has to always be, the derivative always has to be negative, or it always has to be positive. It can't switch inside those intervals. So all we need to do is just take the derivative at some point inside that interval. So we're going to take first interval from negative infinity to 0. We're going to take the derivative at -1. We plug that into the derivative function, not into the original function. So I'm going to use this here. So I'm going to get 3 times -1 squared minus 6 times -1. So that's going to equal 3 times 1 plus 6, which is going to equal 9. That's greater than 0. So the derivative here is always going to be greater than 0. So that means f is increasing in this interval. All right, when we go to the second interval, I take a point inside here, take 1, that's an easy point. And I'm going to look at again, I'm going to look at the derivative at that point. So I'm going to have 3 times 1 squared minus 6 times 1. So that's going to be 3 minus 6, which is -3, which is less than 0. So the derivative there is always going to be negative. And so that is decreasing in that interval. And the last one, I'm going to take a point, 2 to infinity. So let's take 1. Oh, sorry, 1's not in there. So let's not take 1. Let's take 3. So then when I put 3 in there, I get 3 times 3 squared minus 6, 3, right? And so then I get 3 squared is 9. So I get 3 times 9 minus 18. And that's going to be 27 minus 18, which is 9, which is greater than 0. So the derivative inside there is always greater than 0, so it's increasing. Again, we only have to take one point inside those intervals because of the way we made the intervals. As long as we made the intervals by finding the critical points, taking the derivative, setting it equal to 0, and using those critical points as the endpoints of the intervals, then this method will always work. So we can say that f is increasing on the interval from -infinity to 0, union 2 to infinity, and f is decreasing on the interval from 0 to 2. All right. Next, we're going to find out does the function have a local max and min? To find out where f has a local max, we can use either of the two approaches that we talked about before. So let's use the first technique. Okay, we've already figured out where it's increasing and decreasing. That allows us to use that technique a little bit easier than the second approach. Remember, the first approach is if function is increasing and then decreasing, that where it changes, it has a local max. The other approach was to critical number and then look at the second derivative there. And if the second derivative was negative, then at that critical point, then it has a local max. That first approach is easier here. So where is the function increasing? Well, it's increasing like this, negative infinity to 0, and it's decreasing from 0 to 2. Where do we get that? We get that from the work that we did just in the previous part. All right. So that means then that if it's increasing and then decreasing, has a local max at x equals 0. And what's the value of that? Local max value at x equals 0. All I do is I put in 0 into my original function. All right. Again, my original function, just for reference here, since we don't have it on this page, was x cubed minus 3x squared plus 4. So f of 0 would be 0 cubed minus 3 times 0 squared plus 4, which is going to equal 4. So there's my local max value. And that occurs at x equals 2. Likewise, we can find has a local min value and minimum when it's going from decreasing to increasing. And if I go back to the previous chart here, use this orange yellow card here, color, it's decreasing from 0 to 2, and it's increasing from 2 to infinity. So it's decreasing from 0 to 2, and then it's increasing from 2 to infinity. So that tells me that there is going to be a local min at x equals 2, and I'm going to find the local min value at x equals 2. I'm going to take my original function, put in 2, so that's going to give me 2 to the third minus 3 times 2 squared plus 4. So that's going to equal 8 minus 12 plus 4, which equals 0. So that's going to be my local min value. Okay. We could solve this another way. We could find the critical numbers, which were 0 and 2, and then take the second derivative and evaluate the function at the second derivative. Let's just do that. So just another way. Okay, know the critical numbers. We did that earlier. Okay, that were derivative x equals 0. That happened at x equals 0 and 2. And then we look at the second derivative. We haven't done that yet. But if I go back to my function, recall my function was, I'm going to write it down here because we don't have it written. It's x cubed minus 3x squared plus 4. So the first derivative was 3x squared minus 6x. The second derivative is going to be 6x minus 6. Now let's take critical numbers and evaluate the second derivative. So if I put 0 in there, I'm going to have 6 times 0 minus 6, which is negative 6, which is less than 0. When I have less than 0, I've got negatives, the stormtrooper or frowny face, and that gives me a local max. So we have a local max at x equals 0. And notice matches with what we had right here. Local max at x equals 0, local max at x equals 0. And if I take the second derivative now and evaluate it at my other critical number, 2, okay, there. Then when I put 2 in there, I've got second derivative is 6x minus 6, so 6 times 2 minus 6, which is 12 minus 6, which is 6, which is greater than 0. So I've got positive, positive, because it's greater than 0, so I use positive. I got second derivative, so I have 2 of those, smiley face, and when I have that, I've got a local min at x equals 2. Okay, that matches again with what we had up here. Okay, either way works. You have to find local max value and the local min value. You would do it just like you did in the previous problem. You would take that value and plug it, x equals 0 for the local max value, plug it into the function f, figure out what that is, which was 4. To find the local min value, you take x equals 2, where the local min occurs, plug it into my function, f, and you'd get the local min value, just like we did above. Okay, what else can you do here? We can find the intervals of concave up, concave down, which is often just shortened to be intervals of concavity. All right, so to do that, I need to find the second derivative, which we just did. Remember, f was this, x cubed minus 3x squared plus 4. The first derivative we did before was 3x squared minus 6x. The second derivative then is 6x minus 6. So there's the second derivative, and we're going to set the second derivative equal to 0. So we have 6x minus 6 equals 0, and that means then bring the 6 over, divide by x, I get x equals 1. So now I'm going to do intervals, just like I did in the previous one when we were doing the intervals of increasing and decreasing. I have two intervals. I've got negative infinity to 1 and 1 to infinity. How do I get those intervals? Well, I use this number. This tells me how I make up my intervals. All right. And so then we're going to do our little table like we did before, and we're going to look at the second derivative. Just like when we did the intervals for increasing and decreasing, we have these two intervals. I can take any point in there, and whatever works for one point is going to work for all the points because of the way we set up the intervals. So I'm going to take, in this case, the first one, I'm going to take the second derivative at 0. If I plug that in, I'm going to get negative 6, which is less than 0. So I have derivative, and it's less than 0, so I have negative signs, 2 of them. Okay, stormtrooper face or face, and that means it's going to be concave down. If I do second interval from 1 to infinity, I'm going to look at the second derivative at 2, one of the points in between 1 and infinity. And if I do that, we're going to end up with positive 6. We did that earlier. 6 times 2 minus 6, which is 12 minus 6, which is positive 6, which is greater than 0. So I have positive, it's greater than 0, second derivative, so I've got two positives, and I make that into smiley face, and so that's concave up. And I can also ask then, is the inflection point, or any inflection point here, well, it occurs when it goes from concave down to concave up, so occurs at x equals 1. Where does that x equal 1 come from? It comes from where it changes from concave down to concave up, and that happens at 1 right there. If I write that as a point, then going to be here, I know that is 1, so now I'm going to look at f of 1, and when I plug that back into my original function, that was 1, it was x cubed, so 1 cubed minus 3 times x squared, so that's minus 3 times x first, plus 4, that's going to equal 2. So 1 comma 2 is an inflection point. The x equals 1 is where the inflection point occurs for the x value, but the inflection point is this whole part 1 comma 2. Okay, I guess I didn't write this down, but just for summary's sake, it's concave down on negative infinity to 1. Okay, we got up here, and it's concave up on from 1 to infinity. Okay, we've got all those things listed now. And the last thing is we could sketch a graph of this. And how would I do that? Well, I'm going to use the ideas that we have here. We know that at comma 4, 0 comma 4 is a local max, and also 2 comma 0 was a local min. So 1, 2, 3, 4, y-axis, put up a point there, and 1, 2, 3, 4, 5, here's my x-axis. I had a local min at 2 comma 0. And if we go back and we can see, it was increasing from negative infinity to 0. So it's going to be going up like this. Then it was decreasing between 0 and 2. So it's going to go down. And then it's going to go up again because it was increasing from 2 to infinity. And I have my concave down from here, and I have concave up from here. So this is concave up, and this was concave. Okay, do one last example of a type of problem here. And in this problem, f have the derivatives. So you're not told this problem what f is, but you're told what the derivatives are. So f prime is going to be x squared minus 2 over x to the 4th. And the second derivative is going to be 2 times parentheses 4 minus x squared all over x to the fifth. Okay, we're asked what happens at x equals negative square root of 2. All right, so let's plug this into the first derivative. What's the first derivative at x equals negative square root of 2? Well, so I've got negative square root of 2 squared minus 2 over negative square root of 2 to the fourth. So negative square root of 2 squared is going to be 2. So I have 2 minus 2 on the top. And on the bottom, negative square root of 2 to the fourth power is going to be 4. And so I get 0 over 4, which is 0. So if the first derivative equals 0, what does that mean? Well, that means negative square root of 2 is a critical number. Is it a local max or min? I don't have enough information to know yet. It could be a local max, it could be a local min, it could be inflection point. All right, so I need to know what happens at the second derivative. So let's look at the second derivative, negative square root of 2. So I'm going to use my second derivative, which is up here. All right, and I do that, I get 2 times 4 minus negative square root of 2 squared all over negative square root of 2 to the fifth. So in the numerator, I get 2, I get 4 minus, again, negative square root of 2 squared is going to be positive 2, so I get 4 minus 2. And in the denominator, negative 2 to the fifth power, square root of 2 times negative square root of 2 is 2. So I'm going to get times 2 times negative square root of 2. So this is going to be negative 2 square root of 2. We'll figure that all out. And so I can then rewrite this as 4 over, oh, wait a minute, sorry, little mistake there, back here. Let's just do this off to the side. What's negative square root of 2 to the fifth? So that equals negative square root of 2 squared times negative square root of 2 squared times negative square root of 2. Negative 2 square root of 2 is 2. This is 2. And this is going to be negative square root of 2. So I'm going to get 4 times negative square root of 2. So I could write that as negative 4 square root of 2. Okay. It's just like a little brief interruption there. So now I've got going from what we have over here down, I have 2 times 2. So I have 4 on the top over negative 4 over square root of 2. So it doesn't really matter what happened. I can simplify that, but really what's important is whether it's positive or negative. That's going to be negative. So what happens if the second derivative is negative and the first derivative is a critical number? So I've got negative, negative, going to be a frowny face. And in that case, if my first derivative was also a critical number, then it's going to be a local max. The local max at x equals negative square root of 2. All right. Hope that helps you. Have a great day.